Hey, folks. We're continuing our look into rates of change and the beginning of particle motion. So really, this is the kind of first step into the application of derivative, this idea of rates of change and how they affect, or how they can be helpful in helping us, predict what's going to happen. Once you figure out how something's going to change, you can use that information to predict what's likely to happen in the future. Okay, so we're going to start off. We've got this story. Imagine a sphere whose radius is decreasing when the diameter of this sphere is 6 feet with respect to the radius, comma. So then the questions are all after that. So this is kind of a weird way to write it, but we know for all of these stories that the diameter of the sphere is 6 feet. So I'm going to do a little highlighting here. A couple of things that are worth remembering. So our radius is decreasing. Okay, that might come into play later. I don't know exactly what that means right now, but I do know that it's probably going to come into play. And then we know that the diameter of the sphere is 6 feet. Now, this is what we call a moment in time. So what we're going to do is we're going to look at some situations where, or we're going to look at the overall change of the volume of this sphere, and then we're going to look specifically at what's happening when the diameter is 6 feet. So this isn't this doesn't mean that the diameter is always 6 feet. What we're trying to figure out is we're trying to figure out what's happening. Like, for instance, how is the volume of the sphere changing when the diameter is 6 feet? That's going to be different than when the diameter is 5 feet or 4 feet or 3 feet. So this is a moment in time. It doesn't mean you just automatically plug it in. We're just going to want to make sure that we're figuring out what's happening at that moment. Okay, so how fast is the volume of the sphere changing? Explain your result. Mostly explain your result usually just means do a little write-up at the end. How fast is the volume of the sphere? Well, obviously, what do we need to know if we want to figure out anything about the volume of the sphere? Hopefully you said we need to know what the volume formula is for a sphere. So this is worth memorizing. Volume is based on radius. Volume is equal to 4/3 pi r cubed. I don't think I will give that to you. If I remember correctly, I usually have you guys memorize this one. There's a couple of ones that I expect everybody to memorize. Maybe that would be worth it right now to talk about those. Let's put those at the bottom here. So the volume of a sphere is worth memorizing. Then I'll talk more about the surface area in a second. The other things that College Board expects you to know by heart would be area of a circle. Area of a circle is pi r squared. They would expect you to know the circumference of a circle. Circumference of a circle is 2 pi r. Now, I used to always get these two mixed up, but look they always have a pi, they always have an r, and they always have a 2. So how do you decide? How do you remember which one it is? Well, think about what area is. Area is a measure of two dimensions, length and width. So you need to have two r's. You need to have an r for the length and the r for the width of our circle. I know it's kind of weird to talk about length and width when it comes to a circle, but that's kind of the way.
Good morning. I found a set of keys that belongs to a Buick SUV parked in the church parking lot. If you are missing your keys and have parked in the church parking lot this morning,
Yeah, surprise visit from Mr. Rogers there. So the difference between area is two-dimensional, so it needs to have two calculations for radius, where the dimension for a circle is one dimension, for circumference is one-dimensional, so it only needs one radius. I would also expect everybody to know the formula, the area of a triangle Area of a triangle is 1/2 base times height. What else? Area of a rectangle is length times width. So that also is the formula for a square, except the length and the width are the same number. And I'm going to bring this one up now, even though you probably won't remember it. We're going to use it later on. I want to talk about the area of a trapezoid. Area of a trapezoid equals 1/2 base 1 plus base 2 times height. These are all worth memorizing, and there might be more that I'm not thinking of right now. If they come up, I'll add them to our notes. But these are all worth memorizing as you go through. Okay, so now we come back up here. How fast is the volume of the sphere changing? Explain your result. So this is the formula for the volume. Well, if I want to figure out how the volume is changing, I'm going to leave a little note here. I'm going to annotate again. The volume of the sphere is changing. That's a rate of change. That's the rate of change of volume. Well, what's the rate of change of volume called? What do we do to calculate the rate of change? Like, one of the biggest ideas of this whole class is that if you want to figure out a rate of change, you're going to try to do the slope. And sometimes we try to find the slope. We can use the slope formula, but unfortunately, in this case, we want to find the slope for every single radii in this sphere. So that would be the derivative. So that means we want to figure out what is v prime of r. Okay, that's not too bad. We're pretty good with our derivatives at this point, or at least I hope we are. So if this is our function, excuse me, let's derive it. What color do I want to use? Maybe a light purple. So v prime of r is equal to, okay, what type of rule is this? Well, this is nice. This is just a straight up power rule. 4/3 and pi are coefficients, so they're just going to carry on into my as my coefficient. So it's going to be 4/3 pi times, and then I would derive the r cubed. R cubed derivative is 3r squared. And now we can clean this up. The 3 and the divide by 3 would cancel each other out, or you could do 3 times 4 is 12. Divided by 3 leaves you with the 4 pi r squared. Okay, so here's our first OMG moment. Look down below. Volume, surface area. Look at what the formula is. Look at the connection between the volume and the surface area. It turns out that surface area is the derivative of volume. So what I did as a student is I memorized this formula, and then I just remembered that surface area was the derivative. And it's kind of cool because volume is how many dimensions? This is a three-dimensional, let me get a good color here. This is a three-dimensional, someday I'll be good at picking colors. Volume is a measure in 3 dimensions. If I always think of a cube when I think of volume, which is length times width times height. For us, it's radius and radius and radius. Either way, you've got 3 measures of length that are multiplied together. Well, surface area is a 2-dimensional scenario. So the derivative of an x cubed is an x squared. So it's always going to have this kind of pattern. Down here, the same thing. Notice, look at what the circle. This is a connection that you couldn't have made. No teacher could have made this connection with you before you've taken calculus. It's kind of, this is the end of the movie. Calculus is the reason we do all the stuff leading up to calculus, is so that at calculus you kind of see why you did all that junk. But circle is a 2-dimensional, area of a circle is a 2-dimensional measurement. Circumference of a circle is a one-dimensional measurement. And what do you notice? What's the derivative of pi r squared? Well, I'd bump the 2 out in front, 2 times pi times r. So it turns out that the circumference formula for a circle is just the derivative of the area formula. Anyway, so I can't resist talking about some of those connections. I think that those are really interesting. Okay, so what we figured out so far is the volume based on the radius is equal to 4 pi r squared. So now we have a rate of change formula for the volume. What was the question anyway? How fast is the volume of the sphere changing? Well, this is the how fast the volume of the sphere is changing for all radii. We want to figure out, here's where that moment in time comes into play. Now, this is an extra sneaky moment in time because what is our moment? Our moment is when the diameter is 6 feet. We don't care about when the diameter is because we have a volume formula that's based on radius. Well, let's just do a quick remember that diameter is equal twice radius. Therefore, my radius has to be equal to 3 feet. Oh, I should have done this right off the bat. I didn't even catch it until just now. Warning, 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 Will Rogers. You guys don't even get that reference. What are these? I want to do it in a brighter color. What are these? These are units. Units, units, units. That means that my story has to have units, units, units. My answers have to have units, units, units. Okay, so how fast is the volume of the sphere changing? This is the volume formula. Sorry, this is the rate of change formula. The slopes of all the volumes and how they're changing when the radius is 3 feet. So what I want to do is I want to take my volume formula and I want to plug in 3. So what would that look like? V prime of the radius is 3 equals 4 pi times the radius is 3 squared. So we would clean this up. 3 squared is 9. 9 times 4 is 36. So we would get 36 pi. This would be a non-calculator problem, so you wouldn't actually have to go figure out what the 36 times pi is. Okay, now this is the explain your result part. We're going to do a little write-up. So this is a rate of change. So we want to use a phrase. We want to use phrases. Usually, you want to rewrite the story, and then use phrases because this is a rate of change, like increasing or decreasing. So let's see here. The volume is changing. Nope. I always like to say, instead of changing, I like to say increasing or decreasing. You could say changing, by the way. I don't like to. I like to say what it's doing. So this is a positive value. No. I've got to be careful here. What do we know about if the radius is decreasing? That means everything. If the radius is decreasing, what's happening to my volume? If the radius is decreasing, this is a good place to annotate here. If my radius is decreasing, then my volume is decreasing. That makes sense. If my radius is getting smaller, then my volume is also getting smaller. So I want to say the volume is decreasing by 36 pi. That's not good enough because that you got to have units. Okay, so what is the rate of change of volume? So it's how volume is changing over time. So volume, let's go over here and write our units. Okay, so what would be the units for volume? Volume is my radius times our radius times our radius. Our radius is measured in feet, so it'd be feet times feet times feet, which would be feet cubed. Volume prime is the change in volume over the change in radius. Okay, so what would be our change in volume? Well, the change in volume is measured in feet cubed. Radius is measured in feet. Now, this usually doesn't happen. Usually that bottom number is time. But in this case, we've got feet cubed on the top. We've got a feet on the bottom. That means one of our feet cancel, and we're left with feet squared. Okay, so wait a minute. This kind of makes sense. Feet squared is a measure of area, right? And what did we say that the derivative of volume was? The surface area of the sphere. So it does make sense that the volume is decreasing by 36 pi feet cubed per feet, which just ends up being the same as the surface area. Now, this is not enough because it's not always, the volume is not always decreasing by 36 pi feet squared. It's decreasing by 36 pi feet squared when radius r equals 3 feet. This story changes if I say what's happening with the story changes if I said that the diameter of the sphere was 5 feet or 4 feet. If the diameter was at 4 feet at that moment in time, I would plug then a 2 in here. I would get a totally different number. So the volume changes over time. Okay, how fast is the surface area of the sphere changing? Well, what did we just figure out? We've got the surface area formula down here, but I would rather have you think about this as surface area based on radius is the same as the derivative of volume based on radius. That way I only have to memorize one formula. 3 bumps down cancels a 3, 4 pi r squared. So that's the formula for surface area. Now, what we want to know is, let's annotate again. What we're trying to figure out is how fast is the surface area of the sphere changing. So that's looking for the rate of change of surface area. So the rate of change of surface area is the same as the derivative of surface area. So we now need to figure out the derivative of surface area, which is pretty straightforward. We've got this is our surface area formula, 4 pi r squared. So surface area prime would be equal to 8 pi r. So let's talk about the moment that we're trying to figure out the change in surface area. The surface area, the moment we're looking for is when radius is 3 feet. So again, I'm going to plug in 3 So then this would leave me to say that surface area prime at, here we go again, 3 feet is equal to 8 pi times 3, which ends up being 24 pi. Okay, so explain your result just means that we want to do a little bit of a write-up. The surface area, I'm too lazy to write it all the way out. The surface area is, okay, again, you can just write changing if you want, but then you'd have to have a negative in front of this because according to the story, if the radius is decreasing, think logically about what's happening, then the surface area is also decreasing. So the surface area is decreasing by 24 pi. Okay, now I've got to figure out units here. So I'm going to go back over here, surface area prime. So first of all, surface area is measured in feet squared because it's an area. So if I want to figure out the surface area prime, that would be the change in surface area over the change in radius. So surface area is changing by feet squared. Radius is changing by feet. So those would end up with just canceling out, and our unit would be feet. The surface area is decreasing by 24 pi feet when, here's our moment in time, when radius r equals 3 feet. I wonder if I should actually be saying diameter d is equal to 6 feet, but I'm not going to worry too much about that. How fast is the diameter of the sphere changing? Explain your result. So we need to now come up with a formula. Now this isn't given to us, but we can just think logically about it. Oh yeah, we actually did already write it. What's the relationship between diameter and radius? So diameter is equal to 2 radius. Oh, I should write it as a function. Diameter based on radius is 2 radius. So whatever the radius is, the diameter is twice that. So what would this look like? So the first thing I have to do is I want to figure out how the diameter of the sphere is changing. So that's the rate of change of the diameter function, which means the derivative of the diameter function. Derivative is pretty easy in this case. Derivative of 2r is just 2. Now we have to do our little write-up again. The diameter is, okay, again, think it through. If the radius is decreasing, then the diameter is decreasing. That makes sense. If the diameter is decreasing by 2, let's talk units. So I'm going to go back over here and think through the units. So what would be the units for diameter? What is diameter measured in? Diameter is just a one-dimensional distance. So length, maybe I should say. So that would be feet. So diameter prime would equal change in diameter over change in radius. Ooh, this is interesting. Change in diameter is feet. Change in radius is feet. I wonder if you could get away without writing the units. I'm so fearful of not writing the units that I'm going to write the units as feet over feet. 2 feet per feet. The diameter is decreasing by 2 feet per feet when, again, you got to say when this moment is happening, when radius r is equal to 3 feet. Even though in this scenario, I don't think that the diameter will always be changing by that, no matter what moment in time you look at. I was going to get into the next part. I think I'm going to stop here. So this is a pretty short video, but that means we just got a couple more longer ones coming up.